All right, let's get right into it because what we're talking about today sounds like it's straight out of science fiction. We're talking about using a magnet to melt a solid object. Yeah, no heat, no lasers, just a really, really powerful magnetic field. So, how on earth is that even possible? I mean, seriously, think about it for a second. Everything we learn in school tells you that to melt something, you need to add energy, right? Usually as heat. That's what breaks the bonds of a solid and turns it into a liquid. So the idea that you can just put something near a magnet and have it melt, that kind of feels like it breaks a fundamental rule of physics. Well, it turns out the answer is a big, resounding yes. Researchers over at Auburn University did exactly that. They took a very special kind of crystal, ramped up a magnetic field, and just watched it dissolve into a liquid. This isn't some theory. It's a real, groundbreaking experiment, and we are going to break down exactly how they pulled it off. Okay, so to get our heads around this little magic trick, we first need to understand the material they were working with. Because this wasn't your everyday crystal, like ice or salt. Oh no, this was something way more exotic, a plasma crystal.
So what in the world is that? Well, you start with plasma, the fourth state of matter. It's basically an electrified gas of ions and electrons. Then you mix in these tiny solid particles, which scientists just call dust. These little dust particles act like sponges for electrons, soaking them up from the plasma and becoming very, very negatively charged.
And this isn't just some weird thing cooked up in a lab. Dusty plasmas are literally everywhere in the universe. We're talking about the magnificent rings of Saturn, the glowing tails of comets, even those vast, beautiful clouds between the stars. So what's happening in this lab is actually a little window into how the cosmos works.
And making one is, believe it or not, pretty straightforward. Scientists use an electric field to make these dust particles just kind of float inside the plasma. Like we said, the particles get this really strong negative charge, and since we know that like charges repel, they all start pushing each other away until they find a perfect, stable balance, arranging themselves into this beautiful, super-ordered crystal lattice.
So let's just put this side by side. A normal ice crystal is made of water molecules held together by molecular bonds. You melt it with heat. Simple. But a plasma crystal is totally different. It's made of these much bigger microparticles, and they're held together by pure electrostatic repulsion. And this brings us right back to our central mystery. What force, if not heat, can tear these things apart? All right, let's get to the experiment itself. This all went down at Auburn University's Magnetized Dusty Plasma Experiment, or MDPX for short, which, by the way, has a seriously powerful superconducting magnet. So, before they flipped any switches, everything was perfect. These tiny particles settled into what the researchers called a nearly hexagonal crystalline structure. Basically, a perfect, stable, two-dimensional solid, just floating there in the plasma. The particles were only just kind of jiggling around a little bit because of thermal energy. Then, they started cranking up the magnetic field. They gradually increased its strength all the way up to 1.28 Tesla. Now, just to give you some perspective, that is tens of thousands of times stronger than the Earth's magnetic field. And as that field strength grew, they watched the magic happen. The perfect, ordered crystal just started to fall apart. That beautiful long-range order vanished, and the particles started moving around in this disordered, almost chaotic way, exactly like a solid melting into a liquid. Okay, but seeing it is one thing. Science demands proof, right? How could they be absolutely sure that the crystal had actually gone through a real phase transition from solid to liquid and wasn't just, being shaken up a bit? Well, they used a very cool tool called the pair correlation function. Now that sounds complicated, but just think of it as a ruler for orderliness. And this chart shows it all. At zero magnetic field, see that bar? The crystal had a super high order, almost perfect. But as the field ramped up, that order just plummeted, which confirmed it. The structure had dissolved into a liquid-like state. So we know the magnet melted the crystal, but how? This is where it gets really good. The answer is not what you might think. The magnetic field didn't just brute force the particles apart. The actual mechanism is way more subtle and honestly, way more clever. This is the big reveal of the whole experiment. It wasn't about the magnetic force simply overpowering the electrostatic force holding the crystal together. No, instead, the magnet created a totally different kind of force, one that basically tore the crystal apart from the inside out. So here's what happened. Step 1. The magnetic field interacting with the plasma's own electric field created a steady flow of ions. You can picture it like a gentle, constant wind. This wind started pushing on the crystal, and it caused the whole thing to start spinning as one solid, rigid object, just like a vinyl record on a turntable. But as they cranked up the magnetic field, something crucial changed. The rotation stopped being uniform. The inner part of the crystal began to spin at a different speed than the outer part. This is called differential rotation, and that was the key to everything. This difference in rotational speed created this incredible internal stress inside the crystal. And there's a name for that. It's called shear. The best way to picture it is to imagine twisting a deck of cards. See how the cards slide past each other? That exact same force was now happening inside the crystal, with the faster inner layers grinding against the slower outer layers. And that's the whole story. As the researchers themselves put it, this shear created a breaking point. The internal stress just became too much for the electrostatic forces holding the crystal together, and it literally tore itself apart, melting into a liquid. So it wasn't the magnet itself that was the weapon, it was the rotation the magnet created. So this is a fascinating result, no doubt. But what's the bigger picture? Why is melting a tiny crystal in a lab with a magnet such a big deal? Well, this matters for a few huge reasons. First, it shows us a brand new way to control the state of matter, using a mechanical force instead of just dumping in heat. Second, it gives scientists an incredible tool. Because they can watch each individual particle, they can study the physics of melting up close in a way they never could before. And finally, it gives us real clues about how those massive, dusty plasmas behave out in space, shaping things like the rings of Saturn. When you boil it all down, this is a thing to remember. This experiment proved that a mechanical force, in this case shear from rotation, can be used to create the exact same outcome as thermal energy. It broke the bonds of a solid and turned it into a liquid. Force stood in for heat. And that leaves us with a really fascinating thought to end on. If a force that we can see and measure, like rotation, can mimic a fundamental concept like heat, it kind of makes you wonder, doesn't it? What other connections are out there? What other fundamental forces of nature might be hiding in plain sight, just waiting for the right experiment to reveal them?